All right. It seems like they've replaced some lights. It's not what we needed, actually. All right, let's begin. It's a pity that Dr. Pearson couldn't stay longer. He's one of the good ones. You know, how many of you took a class from him? What'd you have? 111? Huh? 102, 111. Yeah, 102 is CAD. You didn't have that from him. Did anybody take circuits from him? Yeah. Too bad. Great guy. All right, so this is your last homework assignment, homework 7B. Looks like I've got homework 7A here. We'll go over some key ideas for that assignment on Tuesday of next week. But we are coasting towards the final exam. Speaking of which, when is the final exam? You tell me. I'm not sure when I should show up. I'm sure it's on the syllabus at some point. Thursday the 15th. All right, I'll be here, I guess. All right.
You can just eat it too if you're going to show up.
I think we'll all be here, right? Okay, so we're going to continue talking about Chapter 7 stuff. This is the most important chapter in the book because this is sort of the foundation that we're going to build on next semester when we start doing hydraulic design. Usually in the curriculum where most people are at when they're taking this class and then going on to hydraulic engineering, that's the first time that they're doing like genuine engineering design that's iterative and that's based on the same kind of programming and the same kind of concepts that you'll need to incorporate when you begin your professional career. So that's always kind of exciting to be a part of. I mean, in a way, I'm jealous that you get to take the class and I don't because hydraulic engineering is a great one. And so this chapter is really important and it's also important because on the final exam it's going to be more heavily weighted than any other section of the course. You know, the exam is going to be cumulative because it has to be. I mean, it would be impossible to give a non-cumulative exam in this class because all of the concepts sort of build on each other. But a disproportionate share of the questions will come from the material since exam 2. All right, well, let's begin by talking about pipe roughness. And here's a table that you haven't seen before. What it illustrates is, it's called the equivalent roughness of different materials. And these are some materials that over time pipes have been made out of. Some of the more common pipe materials these days are galvanized iron, cast iron. Occasionally concrete pipe is used for gravity flow, meaning like sewers and storm sewers. It's pretty uncommon to have concrete piping for pressurized flow. It's kind of strange to think that long ago people used wood for piping, but they did. And I'll dim the lights so you can see the image there. That is a picture of some wood pipe that was held together with a coil of wire, and then I guess it's a little bit like a barrel. You need really excellent craftsmen to be able to make a watertight pipe, and it's probably going to have lots of leaks. But what we're really focusing on here is the equivalent roughness. Now you'll notice the measurements here are in millimeters or in feet, and what it measures is the average diameter if you were going to represent the roughness of the pipe as an equivalent piece of sand, which is a little bit abstract. But let's say, for instance, that we had smooth concrete. Most people have felt smooth concrete. You know, you have sort of a visceral experience of running your fingers over concrete. And so what we're saying is if we were going to represent the roughness of that surface by glued pieces of sand on that surface, it would be the equivalent diameter of those pieces of sand would need to be 0.3 millimeters. And so if you think about the size of a millimeter, then I think you'll probably agree that kind of makes sense. The size of a millimeter versus your finger going over it. And in the case of rough concrete, think about a really rough, maybe like a brush finish concrete. 3 millimeters would be pretty jagged concrete. But the average diameter here, the equivalent roughness, is what we use as the first physical parameter for calculating the F value that needs to go into the Darcy-Weisbach equation. So the Darcy-Weisbach F itself is kind of, it's empirical, and it changes based on flow conditions, and it's not directly related to one physical characteristic, but the beginning point is what is your pipe made out of. And oftentimes, as a hydraulic designer, people will have to change their material selection based on needing to conserve energy, because a pipe like cast iron maybe would have a roughness too high, but wrought iron has a considerably lower equivalent roughness. So remember that epsilon, or sometimes it's known by the variable K sub s, here on the right side of the figure is relative roughness. And what you'll start off with is an understanding of what the pipe is made out of. So if we had, for instance, a pipe that's made out of cast iron, then we'd say our K sub s for cast iron is 0.26 millimeters. And now on this figure, we're going to say what's the diameter of the pipe that we're working with. And one common pipe diameter could be 0.250 meters. And so that is 250 millimeters. All right, so I think most of you have calculators. Can you tell me what would be the K sub s to D for this pipe material and this pipe diameter? Should be pretty close to 1,000? Wait, 1 over 1,000, right? So is it 0.001 roughly? Yeah? All right. So what you do is you start off here on the right axis with the relative roughness, and you find the curve that you're closest to. Or if you're in between values, like if you had 0.0008, then you'd be between these two lines, and you would be equidistant between them regardless of where you were going. So let's say in our case we're following this 0.001, and then on the bottom axis you can see here it's saying Reynolds number. Anyone? It's been a while, but do you remember what is the formula for Reynolds number? There's not a square root. I appreciate you taking a guess. Diameter is in there, yep. Kinematic viscosity, right. That's the way I usually write it. We can also say the absolute viscosity, velocity, diameter divided by density. Or have I got it backwards? I always write it this way. So let's just leave it at that. All right. So we've got Reynolds number. It depends on the velocity, the diameter, and the kinematic viscosity. So kinematic viscosity we can get from knowing the fluid and the temperature. So let's say water at room temperature gives us a kinematic viscosity of about 1 times 10 to the minus 6th meters squared per second. So that is our kinematic viscosity. Diameter of the pipe is just, well, we already said we're using 250 millimeters, but our viscosity is in terms of meters, so we need to be dimensionally consistent because we know that Reynolds number itself is unitless. So we would substitute in 0.25 meters in this instance that we're sort of talking about here. Velocity would just be what is the average speed that the water is going through the pipe. But here's the tricky bit. The velocity that the water is going through the pipe depends on the roughness of the pipe. And that's what we're trying to characterize here, is we're trying to see how rough is the pipe, how much energy is the pipe friction causing to be taken out of the system as water flows from one point to another. So it's actually an iterative process where you have to assume a guess value of velocity. Then you find out, well, if I have this guess value of velocity, what Reynolds number would it give me? If I have that first guess of Reynolds number, what would be my F value? And so we would go from this curve, intersecting some Reynolds number, and then we'd go over to the left axis and look up a friction factor. And then you'd use that friction factor to find out how much head loss there is, and then the amount of head loss would allow you to get a better guess for the velocity. So it's this kind of circular process that begins with a guess.
You said like the roughness has to do with like the velocity, does the static friction have an effect on that at all?
What do you mean?
Like if it's in a plastic fluid, do you affects by static friction?
I just don't know what you mean by static friction.
Something like I heard back in the summer when we were at UNH, but I wasn't really sure about
I'm not sure what they mean either.
what
Yeah.
plastic might put up static friction.
Well, remember that when conditions are static, there's no energy loss. So let's say we've got a tank that is connected by a plastic pipe to another tank. So if they're equal elevation, then there's no driving force, and so there's not going to be there's no flow. And if there's no flow, there's no energy loss, so there can't be any friction. But once it begins to move, that's when the friction is relevant. So let's say if this reservoir on the right has a lower elevation than the reservoir on the left, now water will begin to flow between it, and then the material, whether it's pipe, whether it's cast iron or concrete, that's going to begin to be relevant because if the water's moving to the right, the pipe is pushing on the water to the left. So the material does matter, and when you're picking the F value, the starting point that you use here is in the numerator of the relative roughness. The K sub S is where the pipe material, when we're actually talking about flowing fluids, is incorporated. But we'll spend a while next semester figuring out ways to calculate this F value, the friction factor. Now we love it when conditions are laminar because you can see here on the figure for laminar flow, the friction factor is simply 64 divided by the Reynolds number. But as you know, laminar conditions are pretty uncommon. We wouldn't bother having such a low flow rate through a pipe because it would end up, it would be very uneconomical to have laminar conditions through a pipe. To get the quantity of water you'd need at a subdivision and restricting the flow velocity to that which would cause laminar conditions, I mean, the water would have to be going less than 1 centimeter per second, so you'd need enormous pipes. So, I mean, this is on here just because someone did some research and came up with an equation, not because you'll actually ever use it. But what we will use, this is called a Moody diagram. And it's one of a couple of different methods that we'll use for calculating F values. There are some equations that can do it as well, that can estimate it. But the main thing I want you to keep in mind at this point is that, number one, it's an iterative process because the velocity depends on the roughness, and we don't know the velocity until we know the roughness. But we can't know the roughness unless we know the velocity. But we can't know the velocity unless we know the roughness. You know, like we can go back and forth all day long, but we won't. Yeah.
Can we get the velocity on the flow rate?
The flow rate, yeah. But let's say, back to this example of this. All right. So we have a driving force because the elevation is higher on the left than it is on the right. So there's going to be Q here, but we don't know how much Q. And if we don't know how much Q, then V is also unknown. So the flow rate depends on like how rough this material is acting. And you may be wondering, why does that matter? Why does the roughness depend on how fast the water is going? And it turns out to be partly because if we zoom in on these roughness elements, like here is, you know, like the steel grains, and the water is going past the steel grains, there is a zone. This dashed line represents where the flow is laminar. And so if you have a slow-moving velocity, then you'll have a thick laminar zone, and these roughness elements are kind of buried in the laminar zone. But if you have faster-moving water, then that suppresses the thickness of the laminar zone, so that then these roughness elements are projecting into the turbulent zone, and then they induce a lot more energy loss when these roughness elements are projecting into the turbulent zone. So that's kind of why we can't calculate directly what the effect of the pipe material is until we know how fast the water's going. Because when the water is moving very slow, there's not much energy loss. The pipe isn't resisting as much. But when the water is moving fast, the pipe will resist more, and it resists in a different way too, because of the thickness of the laminar zone. So I'm jumping way ahead of myself, but I'm just so excited about it, I can't resist. One other thing I want to tell you about is this dashed line on the Moody diagram. You'll notice that there is a section where these curves are flat, and then there's a section where they are sloped. And the section where they're flat, it's deeming that the rough turbulent zone. So what that means is when you have rough turbulent flow, it's a kind of flow. When you've got rough turbulent flow, then the F value only depends on the relative roughness. The F value is the same regardless of what is the Reynolds number. But then when you're on the left side of that dashed line in the transitional zone, what that means is that the F value is affected by the flow rate. You know, if you have a high flow rate, then your F value would be one thing. If you've got a low flow rate, then it would be another. So those are the sections of a Moody diagram. And we'll return to this in early January. Let's talk about local losses now. The Moody diagram applies to pipe friction, which is a distributed loss, meaning it acts over the entire length of the pipe. And what we sometimes do is we could calculate how much energy loss there is per meter or per 100 meters of the pipe. But the point is that it's spread out. And in fact, it's not just linear, but it's occurring over the entire circumference of the pipe and the area of the circumference multiplied by the length. So it's a distributed loss. These local losses sometimes are called minor losses, but I mean that's kind of like a put down to these losses, right? To say that they're minor, it's pejorative in a way because I mean they're important, you know. And in fact, if you've got a lot of fittings in a system, they can account for a considerable amount of head loss. And so I try not to call them minor losses. I try to call them local losses. And they're caused when you've got flow going around some sort of an obstacle that induces turbulence. You can see here it's listed as a separation zone where the streamlines were trying to reestablish kind of an ordered pattern. And as they go through the transition, here is a circulation, like an eddy, where the flow is kind of hung up here. And so the effective flow area is more narrow than it otherwise would be because this section of the pipe isn't carrying flow right now. It's just got this circular movement. And so not only is there an energy loss of the circular movement, but also now the flow is choked down through a smaller effective diameter, which means there's more energy loss there as well. So we can measure in the lab a local loss, and you will measure in the lab next week a local loss. You've already done the distributed loss with the pressure gauge and those taps that are a meter apart. Well, next week in the lab what we're going to do is we're going to plug into a couple of different fittings and we're going to measure the delta P that occurs up between the upstream and the downstream tap of a fitting. And then we're going to consider what was the velocity of flow through that fitting and the density of the water. And with that, you can calculate this K value. And a K value is a linear expression of how much energy is lost at a certain spot. And the higher the K value, it means you're going to lose more energy. And what you do when you have a flow path, let's say from a reservoir to your house, you can count up all of the locations where water is either flowing through a valve or going around a bend or there's a change in pipe diameter, and every one of those disturbances has an effect in reducing pressure. And so what you do is you add up all of the K values, it's kind of an accounting thing, add them all up, and then you multiply it by the velocity head. one word of caution is that if you have lots of different pipe diameters, then you're going to have a lot of different flow velocities. So you should only multiply the K values by the velocity that is applicable at the fitting in question. So let's say you've got a reservoir and the pipe comes out big and then it goes to a smaller pipe and then it goes around a bend here and then another bend and then for whatever reason it gets to a large velocity again and it goes through a large bend like that. So what you need to do is these K values they'll be listed. You know, here's a K value 2.6, here's one 0.7, here's a K value 1.0. The K value that you will be using has to apply to the velocity at that location. And so you can't just add up all of the K values and then multiply that by the velocity head in the first pipe because there was a lot of different velocity heads. Yes?
Where you have that separation that is turbulent there,
Uh-huh.
you have the area and flows are turbulent.
What happens to this area? I think the separation zone gets bigger as the velocity increases, and that's part of why we see a greater energy loss and a greater pressure change when the velocity goes up, is because the separation zone gets bigger and it's kind of choking the effective flow area even more.
Can we see scouring in the separation zone?
It's possible, yeah. Yeah, there can be scouring of the pipe. All right, so if you brought your binoculars, you can see this table, and we've got different types of local losses. So here is a pipe expansion, and it's kind of interesting to note that they're even keeping track of the angle that defines how gradual the transition is. And so let's compare two different angles. The first is a 20-degree angle, the other is 180. And 180 means an abrupt transition, meaning that it is a small pipe immediately going to a large pipe instead of what's pictured here. Like what's pictured would maybe be a 20-degree angle, and then what's here on the screen would be 180. So tell me, why does it make sense that the K value would be higher generally here for the 180 degree instead of lower for the 20 degree? Why does that make physical sense?
The water's not going to go, straight up as soon as it enters that center pipe.
Okay.
It's that much friction from the outside of the inside of the pipe.
Right. Exactly. So anything we can do to make the transition more gradual and to help order the flow will reduce the amount of energy loss. And so 180 degrees is a very abrupt transition, so the K values are higher. Now here, D1 to D2 is telling you that the bigger the difference in the pipe diameters, then there can also be an effect on energy loss there. So for instance, 0.20, what that's saying is that D1 would be, for maybe an example, 2 centimeters, D2 would be 10 centimeters. So you'd have more energy loss from that than you would if the two diameters are about the same, 8 centimeters going into a 10 centimeter. So an abrupt transition, meaning a really small pipe going to a really large one, you're going to have more energy loss than two pipes that are roughly the same size. So that kind of fits in with the theme, is that anything that's an extreme change is going to extract more energy from the system. The same thing is true with this miter bend here. What they're saying is you can put these vanes into a miter bend, which is a very abrupt transition. And if you don't have vanes, you can expect 1.1 times the velocity head to be lost there. So you find out the velocity head simply by multiplying the velocity squared divided by 2g. Multiply that by 1.1, and that tells you how much energy is lost in an abrupt 90-degree change. But with these vanes in here to kind of redirect the flow and smooth the transition, you can really save a lot of energy that way. Now the smooth bend is kind of an interesting comparison because for one thing, it's a lot less energy loss than compared to the abrupt 90-degree miter bend. You notice these K values are lower, but their minimum is at a radius to diameter of 4. So that means the least energy loss is when this radius of curvature is about 4 times the pipe diameter. But then it's a little counterintuitive because you'd think that an even more gradual transition would reduce the K value even further. But that ends up not being the case. That if you have a really gradual transition, like a 10 radius of curvature to diameter ratio, then the K value has gone up again to 0.32. And the reason for that is that if you have too gradual of a transition, then you're adding pipe length. And so they're kind of incorporating some friction losses into that as well. It's not that the local loss itself is any more abrupt. It's just that you're making the bend pretty lengthy. Yes?
Going to the example on the board, what if the D1 was larger than D2?
Right. So if it's decreasing rather than increasing. Yeah, there's another table that has similar values. They're not the same as this, but there's another table that has D1 to D2, and you'd apply it in the same way. One thing I'll point out is that the velocity that you're supposed to use, because you've got two different velocities, right? You've got the entering velocity and the exit velocity in this transition, like for this expansion here. You've got the fast flow where the diameter is small, and then the slow velocity where the diameter is big. You're supposed to multiply the velocity head at the inlet pipe by these K values. And so they're showing you here that it's V1 that these K values are based on. And so anytime you have a transition and a table giving you K values, the table itself should indicate whether you're using the inlet or the exit velocity from the transition. All right, here is a list of fittings. A globe valve, an angle valve, a gate valve. We'll see some of those valves in the lab. On the pipe rack, we've got different types of valves, and we'll measure how much energy loss there is between them. And I've got some diagrams. When we learn more about fittings next semester, we'll actually sort of look at cutaways of these different types of valves and figure out why a globe valve extracts so much energy, 10 times the velocity head, compared to a gate valve. You know, and the short answer to that is that a globe valve is causing the flow to change direction so many times. What it really is the water is coming in to something like this, and with a globe valve the water will go down and then it will go up and then it will go out. And just the way a plunger goes into the system is it's trying to seal an opening in kind of a circuitous route. So the flow changing direction so many times will have a K value of 10, whereas a gate valve is essentially a straight piece of pipe that a gate can be dropped down into. So when it's all the way open, the flow just goes past and there's maybe a little bit of disturbance here at the opening where the gate would be dropped in. But there's a much lower reduction in energy because of the gate valve being wide open. So next week in lab we're going to calculate some K values and we'll compare it to these published K values. See how the textbook K compares to what we observe in the lab. Any questions before we move on? All right. Here is an expansion. One way to estimate the head loss in an expansion is just by the difference in velocities. So you'll notice here you're saying V1 minus V2, so the difference in velocity squared divided by 2g. And we'll test that out in the lab as well. Because in the pipe rack, we've got a couple of the pipes where it's a different diameter upstream and downstream, so we can see what the effect of energy loss in the expansion is. If you have water going into a reservoir, then you lose all of the velocity head. And this is kind of an interesting thing that we have to be aware of when we do energy grade line diagrams. Back to our drawing of a reservoir here. Think about the water that's moving through this pipe. Energy can be in 3 locations. Do you remember, I've said this before, where are the 3 locations that energy can be? Not quite. I'm talking about like more abstract, not like physical location. I'm talking about when we write the energy equation, what are the 3 terms that we usually start off with? Before we talk about the turbine or the pump or the head loss, what are the other 3 terms that were there when it was just the Bernoulli's equation? Pressure head, elevation head, and velocity head. All right. When water is flowing through a system, these are the only 3 places the energy can be. And so if we've got this location at the top of the reservoir here, there's lots of Z, but there's no velocity head and there's no pressure. So the energy here is existing as elevation. And then down here, less of the energy is as elevation. You know, if we use the bottom of the tank as our Z datum. So now there's a little bit of energy as elevation, but where's most of the energy? Pressure, right. What about when we get into here? Where's the energy at that point? It's in actually 3 places because it's going to have velocity, yes, it's moving, but not all of the energy is as velocity because it still has pressure too. You know, even though energy is decreasing in the direction of flow, there's still a fair amount of static head above it. And so the 3 places the energy can be is pressure, elevation, and velocity. When you have water that's going into a tank like this, just before you go into the tank, in the pipe, you've got velocity head. So there's this energy, V squared divided by 2G, right here. As soon as you go out of the pipe, that energy just vanishes. It's gone. It's lost forever. It's the water sort of exits and diffuses into that tank, and so the velocity head energy isn't recovered as additional pressure. It's just it's a loss that has to be accounted for. And so that's here where we're saying as a discharge goes into a reservoir, then you've got a local loss equal to the velocity head. And at an inlet, what we usually see is that as water goes into a pipe, there's a loss there as well. But it's usually just 0.5 V squared divided by 2G, unless it is a pipe that extends into a reservoir like that, in which case it would be closer to 1. And it's all related to the amount of energy that is required to start accelerating the water, because on this side the water is motionless, and once we're inside the pipe the water is moving, and so there has to be some energy exerted as the water speeds up and enters the pipe. So there are entrance losses and exit losses. All right. You're going to have a question on the exam that uses grade lines. And I love these questions because they're so easy to grade. And, you know, that's important. My comfort and enjoyment is paramount when I'm writing the exams, right? No, not really. But these are easy to grade and they're actually easy to solve too. So I think that you're going to like these problems as much as I do. What this is it's a visual representation of where the energy is and how much energy there is. And so what we're looking at is a tank of water, and pipe is coming out of the tank, and then at the end of the pipe there is a jet of water. So the water is just flowing out with some continuing speed. It hasn't yet started to fall downward, but it does. At the top of the tank is the energy grade line and the hydraulic grade line. It's at the water surface there. And EGL is what abbreviation we're using for energy grade line. And the energy grade line consists of the sum of these 3 terms. The energy grade line is the pressure head, the elevation head, and the velocity head. By contrast, the hydraulic grade line, HGL, is only the pressure head and the elevation head. The velocity head is excluded from HGL. So both of these can be calculated, and I think you did that in the Bernoulli lab. You know, through the Venturi, you did a graph of EGL and HGL. So let's look at some of the aspects of this picture and try and discern what these dashed lines are telling us. All right. Here is a piezometer. We cut a hole in the pipe and attached a tube to it, and the water level is rising in that pipe to a level that indicates what's the pressure in the pipe. And so that's a piezometer, this first tube on the left that we see. And the water level is rising to a certain elevation that is the HGL. And so why is it that as we move towards the right in the pipe that the HGL is getting lower and lower? What's causing that? What is it? Okay. It turns out that the velocity is the same, remember. So the speed of the water has to be the same because we have 1 liter coming in, 1 liter goes out. And so the velocity isn't changing. The velocity is constant, but we are continuing to lose energy because of the velocity. So depending on how you think of it, the EGL is decreasing because of frictional losses. I think is the important thing that the slope of this line indicates how extreme the friction losses are. And so a really steep slope means you're losing lots of energy because of friction losses. And if the slope of the HGL is relatively constant, if it's a shallow slope, then that means you're not losing very much energy. The EGL is always above the HGL, always above, unless, like in the case of a reservoir, they're the same thing. Why is it in the reservoir that the EGL and the HGL are the same? Yeah, there's no velocity in the reservoir. Very good. The water is motionless at the surface of the reservoir. And of course, the EGL is at the surface of the reservoir because there's no pressure either. There's no pressure and there's no velocity, so all of the energy is existing here as Z, all right, at the reservoir. So they're sloping downward because of pipe friction. Why is it that these two are parallel? Anyone want to take a stab at that? Okay, perfect. Yeah, he says at every location the only difference is velocity. So the gap between them, you'll notice here, it's saying the gap is the velocity head, v squared divided by 2g. And they're saying v2 squared because this is location 2. So the v squared divided by 2g, that physical distance between the EGL and the HGL is because of the velocity head. And now here, this pipe, the one on the right, with the little nozzle that's directed into the direction of flow, what they're trying to show you here is that if the water is flowing along and the streamline intercepts this opening, it's going to push the water a little bit higher up. And so see how even though it's towards the right and the lines are falling, the water level is a little bit higher. And the reason for the difference is the added energy that at the opening of this tube, that added energy that was as the velocity head has been converted into a little bit of extra pressure at the stagnation point. Similar to a pitot tube. We've talked about pitot tubes before. Why is at the opening, why is it that the EGL is above the water surface? You're on the right track. It still has velocity head because the water's still moving. Remember that the EGL is above the water when the water is moving. Because the physical location of the water, if you've got a free surface of water, then that means there's no pressure. And so the physical location of the water is the Z. And so HGL is just going to be where the water is. And EGL is above the water surface by the distance that's related to the velocity head. So the water's still moving, but EGL will be above it. Now, whoever created this figure, I think, was a little bit sloppy, because they should have had the HGL terminate at the end of the pipe. But we'll have a chance to get more precise when we do some drawings on our own today. Any questions? Let's look at pictures. Here's a pump. Look what a pump does to the EGL and the HGL. It's a straight vertical line. It's not a crooked line. It just instantly adds pressure. That's what a pump does. A pump does not add velocity, not directly. By adding additional pressure, that may speed up the flow of water compared to what was happening before the pump was operating. But it's not like when you've got a 4-inch pipe coming in and a 4-inch pipe going out. You can't have faster water in the outflow than you had in the inflow. That would violate continuity. So the velocities have to be the same if the diameters are the same. So this pump isn't adding energy as velocity, and it looks like maybe the outflow pipe is a little bit higher in elevation. So remember, the only 3 places that energy can be are velocity, elevation, or pressure. So what this is actually doing is it's having an instantaneous increase in pressure. From one side of the impeller to the other, pressure is increasing. And so since the pressure head term is in both EGL and HGL, there's this vertical line. And then the line is sloping downward again. And remind me, what does the slope of this line indicate? Friction losses. And the slope before the pump and after the pump is the same, because it's presumably the same pipe material and the same diameter, so these slopes are equal. EGL is always above HGL. So that's how you draw a pump. If you ever face a situation where you need to draw what happens to these with a pump. Maybe you'll face such a situation. All right. Here is a turbine, and in this turbine, you can see that it does the opposite of a pump. A pump the line was going up. Now here, the line is going down. And flow in this diagram is from the left towards the right. So head is given up to the turbine. That means there's a big reduction in the amount of energy that's available. Now, the EGL and the HGL are both at the tank surface to begin with. And then there's this point at which energy is being exchanged because the water is speeding up, and so you have to have some of the energy go into the acceleration, and so the EGL and the HGL diverge during this entrance here. That's what this little line is showing. And it's sloped downward because there's friction losses, then you lose a lot instantly. And now this is a bit odd. You'll notice that here the HGL is actually going up. Anyone want to speculate why there's like an upward slope to that HGL? Yes? Elevation? No? It's not related to elevation. Look at the pipe. So what's happening to the velocity of the flow here? The velocity is decreasing because the diameter is getting bigger, so the velocity is slowing down. So if the velocity is getting lower, what is happening to the pressure? The pressure is going higher. And so pressure head is one of the terms in HGL. And so that's why this HGL term is going up, is you're having an exchange of velocity is turning into more pressure as the diameter gets larger and larger. So that's what you need to keep in mind about that. Now, again, whoever made this figure, I think, was a little bit sloppy because the EGL should be above the tank, and then there's an instant loss of the energy, because we've already talked about how you lose the velocity head as soon as the water comes into a reservoir. So I guess maybe it's just that the diameter is so big by the time it gets to the reservoir that the energy loss is minor, but I do like to point that out. Okay, a similar effect here. We have a nozzle, meaning that if the velocity is increasing, then there's going to be more energy loss. So see how the HGL is getting smaller because pressure is being exchanged for additional velocity in this section. So you're losing HGL. One other thing to point out about this is that the slope of the EGL is getting steeper. You notice how it's relatively flat here, and then it gets a little bit steeper? So why is that? Why did the slope get a little bit steeper in that section? Maybe. I guess it's partly local losses and it's part friction because it does happen at kind of an isolated location, but the frictional losses are going to become more extreme as well because anytime you've got a higher velocity, then the friction losses are greater. And I think that's illustrated on this next figure. Okay, look at the two different slopes of the EGL back when the pipe was big diameter on the left compared to when the pipe is a small diameter on the right. So for the small diameter pipe, the things that you would need to include in the drawing of this, you'd need to have the slope being steeper for the small pipe. You'd need to have the gap further apart. Why is that? Why is that the gap of these two lines is further apart for the fast-moving flow? The velocity increases, right. And this gap is related to the velocity head. So that's an important characteristic. Another is now we finally see someone who knew how to properly represent the head loss at the outlet. So you've got this EGL that instantly, it was above the water surface and then suddenly all that energy is gone. So here it's showing like these little blue lines in the tank. That's kind of showing you like the inflow is diffusing into the tank and it's just all the energy that existed as velocity head is just lost. And so this is the EGL representation of that loss as the line was above, now is below. The other thing I want to point out is that the HGL should terminate at the water surface. Because think about where is the energy in the HGL. The HGL is talking about the elevation head and the pressure head. And so on inside of the pipe compared to just on the outside of the pipe, there really isn't much of a change in the elevation, no change in that. And the pressure as well is going to be about the same. There will be a little bit of pressure change due to pipe friction over whatever minuscule distance we're talking about. But that's why you should always have the HGL terminate at the liquid surface. The EGL should always be above it when you have it coming into an open tank like that. Any questions? All right. It's kind of interesting to point out that the EGL and the HGL are independent of the physical location of the pipe. It doesn't matter if the pipe is going side to side. It doesn't matter if the pipe is going up or down. But the EGL and the HGL just have this continual downward march related to the energy loss due to pipe friction. Now the pressure in the pipe is going to be changing, but there can be an exchange between elevation and pressure that the EGL and the HGL won't see. That's occurring inside the pipe. So think about here at this high point in the pipe. You'll actually have the pressure in that is going to be negative. When we're talking about the gauge pressure would be negative. Because if you have the physical location of the pipe above the HGL, what that means is you've got a lot of energy as Z, you've got a lot of elevation head, but not very much pressure head. And in fact, the pressure head's negative. So if you cut a hole in the pipe here, it would actually start sucking air in. Rather than water squirting out, the air would start to go in. Any place that the pipe is above the HGL. All right, so again, here are the key things that you need to include in the drawing. You need to include the EGL and the HGL at the water surface, this transition where the EGL and the HGL begin to diverge. The slope of the line is dependent on the pipe diameter because the pipe diameter affects the velocity and the velocity affects the rate of energy loss. And then you need to make sure that you have the line above the water surface if there's a jet out like that. All right, so I want to show you, go ahead.
Is there any differences when you have a problem like this and you open the atmosphere or a closed space?
That's a great question. So let's say we had an enclosed tank on the left. Then yes, there would be a difference because the water surface wouldn't indicate where the HGL is. If there was like a cap in that and they'd pressurized it, the HGL would be above the water surface, and so would the EGL, since the EGL also includes the pressure head.
Do we have to worry about that as well?
I want you to worry as much as possible. So yes, worry about that. I won't give you any problems related to it, but I do want you to worry about it. I like the idea of you sitting at home worrying about that.
Didn't know if you throw a curveball on the exam like that.
Well, that's a great idea. Maybe I will. Well, now that we've talked about it, it wouldn't be a curveball though, right? So I'll have to think of something else.
Still have it spelled out.
All right. Here's what I'd like you to do. I have a drawing here that shows you a reservoir on the left, a reservoir on the right. And I'd like you to try drawing the EGL and the HGL. So I hope you have some sort of a straight edge. You know, a credit card will work fine if you don't have a ruler with you. There's also a problem on the back side that has a new element for you to try. Now, this is an iterative thing, so don't draw in ink unless you're really confident. But this is the sort of thing where I think that most of you you'll have to erase and start over again because you're going to have different slopes, you're going to have local losses, outlet at the tank, inlet losses, and so on. So I want to give you a chance to try drawing these, and then we'll look at the solution in just a moment. All right, so here's my take on it. Now, you know, these drawings are more qualitative than quantitative. This is not to scale necessarily, but it's relatively correct, meaning that the velocity in the first pipe section is faster than the velocity in the second pipe section. And that's why I've got the EGL and the HGL further apart in the first segment and closer together in the second segment. And then the other thing is the slope of the line is steeper in the first segment compared to the second. Now, what about this? Is this just because I can't match them up? You know, it's not a mistake. It's actually energy loss due to the transition. And so both the EGL and the HGL are going to decrease. Now, depending on what scale you drew them to, you could say, well, but you've got lots of velocity head here and more pressure head, you know, the Bernoulli effect of your exchanging velocity for pressure. So it's possible that your EGL, you could draw this correctly, where the EGL is decreasing, but the HGL is higher. But here I said that the magnitude of the energy loss at the pipe diameter change is larger than any increase in HGL. Yeah. Yeah, why'd they have it droop down like that? We don't know. Yeah, dramatic effect, or maybe there was an obstacle like a big rock in the way. anyways, the point is that the EGL and the HGL are unaffected by the pipe's physical location. They're affected by the frictional losses, they're affected by the diameter changes, local losses, but they're not affected by the physical location of the pipe. All right, so there's also one on the back, and this one's even trickier because there's a triangle and a circle on top of the triangle. I'm not telling you what that represents because I want you to think, what does it have to represent? All right? Oh boy. Don't forget to label the lines EGL on top of the HGL. One of these drawings is never complete unless you've labeled what the lines are. So we've got the EGL and the HGL starting at the tank on the left at the water surface. There's this induction point where they get further apart. Looks like I didn't draw very parallel though. I should have made that a little better. But it's steeper here on the left than on the right because this is the small pipe, that's the big pipe. Also, the distance is greater apart because you've got more velocity head on the left than you do on the right. Any questions? That's a great question, yeah. As drawn here, we could have cavitation because the pump is above the HGL, so it all depends on the temperature of the water. You know, because we have to be further away from it than the value of the vapor pressure. So there is a risk of cavitation in that pump.
Is the HGL supposed to be lower than the pump?
No, it's just that's, well, I wouldn't say poor. I mean, got to give myself a little. No, it's just, it didn't have to be like that height of a line. You know, these are qualitative drawings, and so there definitely is some wiggle room. All right, so here's where we're headed. Homework 7B is the last thing that you have hanging over you, besides that enormous exam, but I'll see you next week.